Okay, so you may recall that we proved earlier in one of the earlier lectures that the connectivity of graphs is not a first order definable. Right? So we proved it using an application of compactness theorem. But suppose we assume that we are only looking at finite models. So if you look at the finite models alone, if you go back to your proof, we can see that our proof fails. But uh, but like, can you say something further about this? In fact, we can. In fact, we can say that compactness theorem fails for finite models. So here is the theorem which states exactly the same thing, that there is a theory T such that T has no finite models, and every finite subset of T has a finite model. Okay, so you have a theory which has no finite models, but every subset has a finite model. So theory is basically a collection of sentences. Okay, so now how do you prove this? Well, you take let us say the language L with empty vocabulary, and you define formula phi n to be saying that there is at least n distinct elements in the universe. Okay, so phi n is there exists x1, there exists x2, etc. There exists xn. Conjunction of negation xi is equal to xj, I not equal to j. Now let T be the theory which is the collection of all phi n greater than equal to 2. Now, T has no finite model, right? That is very clear. And every finite subset, on the other hand, has a finite model, because you take any finite subset, there is a large enough n0 such that larger than n0, right? Your phi n is not part of T, right? So therefore, if you have at least n0 plus 1 elements, then it is not contradicting any of the formulas, right? So therefore, that is a model. So there is a finite model for every finite subset. On the other hand, there is no finite model for T itself. So therefore, compactness theorem doesn't hold for just finite models. Okay. Now let us define a property. Let's say evenness for a structure. So we say that a structure mu is even if the number of distinct elements in the base set is even, right? Cardinality of M mod 2 is 0. Now let us say that you have the language with empty vocabulary, then we say that even is not first order definable. Okay, the property is not first order definable. So how do you prove that even is not first order definable? Let us say that you have some formula phi which defines evenness. Okay, so suppose phi defines even, then let us say that T1 is a theory which is obtained by taking the formula phi union with the phi k, where phi k is the formula that we defined in the previous page, right? There is at least k distinct elements, okay, and k is at least 2. So we collect and this is our T1. Now T2 is the formula set negation phi union phi k is at least 2. I think I must have written greater than or equal to 2 here. It doesn't matter. So T2 is the theory that negation phi union phi k. Now by compactness theorem, both are consistent, right? Because every finite subset of either of these has a model, right? Now the theories both have only infinite models, right? There are no finite models because both of them are consistent. By compactness there is a model, but that is not going to be a finite model. So there is models of infinite cardinality. But on the other hand, we started with the language with empty vocabulary, which means that our formulas are countable, and therefore by Lowenheim's column theorem, right, the first theorem that we proved, both of these theories have countable models, right? Let us say mu1 and mu2. Now mu1 and mu2 are countable models, but since the vocabulary is empty, there is no relation or functions, anything, nothing we have defined. So basically what it says is that the structures of these models, right, of this these theories are basically just sets, right? There is nothing else there, right? There is no relation that we have defined. So therefore, these two things are just sets, right? So mu1 and mu2 are sets, and they have cardinality which is countable infinite, right? They are infinite and countable. So there is precisely one kind of infinity, and therefore they are isomorphic, right? So they are countable infinite sets, and therefore they are isomorphic. So what we are saying is that we have theory T1 and theory T2, which has models mu1 and mu2, and mu1 is isomorphic to mu2 are sets, right? They are sets, therefore isomorphic. But now we are saying that mu1 models phi and mu2 models negation phi. But we said that two models are isomorphic, they must satisfy the same formulas. But here one is modeling phi and one is modeling negation phi, right? So therefore this is not this is a contradiction, right? This is not possible. So therefore we can say that the property of evenness is not first order definable. Okay, so we have we have shown that some properties are not first order definable. Okay, now suppose you want to go a little further. Okay, suppose you want to say that some many properties like this we want to show this. So how do you come up with a way to prove something like this? So so one of the reasons that we want to ask this is that, like, for example, suppose you take a language not with empty vocabulary, but with let's say relation symbol like total order, less than relation, right, which defines a total order. Now in such a case, okay, we can still use some similar argument to say that, like, there are two infinite models, right, of cardinality, like, countable infinite models, right, mu1 and mu2. But now, so these are linear orders, right? But now the thing is that you can have non-isomorphic linear orders of the same cardinality, right, for infinite sets. So therefore for example, like, if you want to think about, let us say that the natural numbers with the with the order less than, right, with a strict linear order. But now this linear order is different from an isomorphic linear order over the over the rationals q less than, right, because one is dense, right, you can always find an element in between any two. On the other hand, that is not possible in the case of natural numbers, right. So we see that they are actually different, right? They are not really isomorphic, because one is having some property denseness and the other does not have. But now how do you try to prove something like this, right? Or like anything like that. Like suppose you want to, then we need some other kind of technique. Now one can think about like possibilities, and there is one very interesting game which can help in some cases at least. Okay, it's called Ehrenfeucht. I think there is a T missing. Phrase game. Okay, it's called EF games. I cannot even read the word because it's in German. Okay, I don't really know how to pronounce it. So So there is the spelling is I think F-U-C-S-T also. Okay, Ehrenfeucht and phrase games. So these are two people. So I already asked you to read as an assignment, phrase theorem, which basically is an algebraic characterization of elementary equivalence. Now, so with the game that Ehrenfeucht defined, there is a nice connection between these two things, Ehrenfeucht and phrase, and therefore it actually helps. One of them gives the idea how to come up with a strategy, and the other actually makes it formal and helps you to come up with the actual numbers or the choices that we want to use to show something is not definable, something is definable. Okay. So something like that. We will not go much into detail, but just to see some examples of this and try to understand, we can give some questions related to this as exercises or as part of your assignments. But mostly, we will spend very little time on this. Okay. So the idea is to prove that a property P is not expressible in logic. Let's say L. Now, as we noted, like you may be able to say that there are two structures which have the same cardinality, right? But they may not be isomorphic, right? Now, how do you proceed in such situations? Okay. So the idea is to partition the sentences in the language L to countably many classes, right? L0, L1, L2, etc. Lk, and find two families of structures. Let us say AK. For every natural number k, you have a family AK and another family BK, such that AK models phi if and only if BK models phi for every phi in LK, and AK has property P while BK does not have. If you can show something like this, right, that for every property phi in LK, right, AK models phi if and only BK models phi, but AK has a property which BK does not have, then of course the property is not definable in L, right? That is the general idea. Okay. So what is this game? So an EF game is basically a two-player game. So there are two players. One is called spoiler and one is called duplicator. Okay. I mean you can call it player one, player two, whatever you want. But the one nice way to look at it is one is called spoiler and the other is duplicate. And there are two structures A and B. So this these structures are the game boards where the game is actually being played. So how do you play the game, right? So the idea of spoiler is to show that A and B are different structures, okay, and duplicator want to show that A and B are the same. Now, so the play is as follows: they play a fixed number of rounds. Okay, so we define a priori that we are going to play, let's say k rounds or 10 rounds or r rounds, whatever, right? So we fix a number and say that we will play at most this many rounds, and winning will be defined based on whether somebody reaches a particular situation, right? Whether spoiler wins or duplicator wins, depending on the situation after these many steps. Okay. So yeah, so that is the idea of the game. Okay. Now, so what is the how the game is played? Like spoiler, in each of his move, right? Each time he is get a chance to play, the first round or second round, any round, he picks a structure either A or B. Right? Every round he can choose differently if he wants, or he can choose the same if he wants. Right? So it doesn't matter. So he can choose. So every round or the beginning, the spoiler, right, the player one picks some structure. Let's say A or B. Now once he picks a structure, so he makes a move by picking one element from the chosen structure. Right? So suppose he picked A, then he has to select some element, let's say small a in A. If he chose B, then he has to pick an element from B. Now, once spoiler picks an element, then the duplicator picks an element in the other structure. Okay. Replicator has to pick from the other structure. So, this is how the game proceeds. Now, to decide the conclusion, we need another concept which we will define in the next page. So here is something like this, how the game proceeds. Like let's say the spoiler picks A1, right? Like from the first this spoiler is the guy with the sharp dot, and the duplicator is the one with the let's say star. Okay, so spoiler picks the element A1, and then the duplicator picks B1. Okay, then spoiler decides, okay, I will go to structure B and select an element B2 from there. Then correspondingly duplicator picks an element A2. Then again spoiler says that, okay, I will stick with B now, I will pick one element B3 from B. Then correspondingly an A3 is picked from A by duplicator. So this way it goes up to, let us say, K or T steps. Now to see what is going on, we want this idea of what is called partial isomorphism. Suppose you have two structures A and B over a language L. Now we will assume that L has no function symbols, that it is basically a relational language, which means that you can have relation symbols, and many of the functions can be defined with relations, right? That is how we define some of the things. So we will assume that there are no function symbols and we have only a relational vocabulary. Now let us denote by a bar the tuple A1 to An, and by B bar the tuple B1 to Bn. Okay, so some two n tuples N, A and B. Then then the ordered pair A bar comma B bar defines a partial isomorphism between A and B. Okay, if for every I and j, right, Ai is equal to Aj if and only if Bi is equal to Bj, right. So if if Ai is picked and Bi is picked, and in case Ai and Bi are the same, right. What I want to say is that Ai is picked in some step and Aj is picked in another step, right, by either of them, right. Like these two elements were picked by during the play. Then correspondingly you had a Bi and Bj, right. So now if Ai is equal to Aj, right, you are allowed to pick the same element again if you want, right, just to the spoiler, let's say, picks element 1 in the first round, then that guy picks some element from the other side, then this guy picks element, let's say 5 or something, and then that guy picks something. Now he can pick again element 1 if he wants or something like that. That's not a that is still allowed, right. So now what we are saying is that if A is equal to Aj, then Ba must be equal to Bj, right. And for every constant in the language, and so we have only gone n steps, right, in the moves, right, n moves only we have made. So A is equal to C raised to A if and only if B is equal to C raised to B, right. If A is mapped to some constant, right, then constant whose interpretation under the structure A, right, is Ai, right. Then that same constant, right, because it's constant, right, that is mapped under B must be is equal to Ba. And for every k relation, let's say R, and every set, let's say I1, I2, etc., Ik from 1 to n, right. Ai1 to Aik, that tuple belongs to Ra if and only if the corresponding tuple Bi1 to Bik is in RB. So this is kind of like saying that these structures from the current information that we have are basically identical, right? If you are looking at only the relations between those guys that we have picked, those relations are the same, right, in both sides. If you are talking about, for example, let us say two graphs, right, what we are saying is that the induced subgraph by the chosen vertices, right, in the set A, in the structure A, is basically isomorphic to the induced subgraph chosen by the vertices in B. Right. So that is precisely what partial isomorphism says. Okay. Now let's say that C1 to CL be some constants in L, and C bar is the tuple C1 to CL, right? You take all the constants in L, right, and form this tuple C1 to CL. Then A bar comma B bar is a winning position for the duplicator if the ordered pair like formed by A bar and the C bar power A is basically each of the elements power A, right? Like the what you call like the interpretation of Ci under the structure A, right? Ci raised to A. So C bar raised to A is C1 raised to A, etc. Cl raised to A, right? So that tuple. So A bar and C bar power A and B bar comma C bar power B is a partial isomorphism from A to B. Okay. Then suppose the duplicator after the n moves, these structures A and B are you know are isomorphic after this n steps, right? Basically so we will say that the chosen subset of elements, right, form there is an isomorphism between those. Then we say it's A is n equivalent to B. Okay, which means that within n steps the duplicator, the spoiler cannot defeat the duplicator, right? Spoiler cannot show that they are different in n steps. In that case, which means that there is a partial isomorphism of this tuple A1 to An, right, and B1 to Bn. Then we say, we write A n equivalent to B, and then in that case the duplicator has an end round winning strategy. Okay, so the duplicator has a winning strategy in n rounds if after n rounds spoiler will not be force him to show that the structures are not isomorphic. Right? So any choice of n elements from the set, whatever the sets, right, any choice, the duplicator has a choice of n elements so that the structures are basically isomorphic. Okay, so even though spoiler has chosen an element, they may not be distinct. So therefore, in the isomorphism, right, the substructure may not have n element. Right? It can have at most n, but it may not be exactly n. That is okay. But the partial isomorphism is still there. So if there is no way he can show that they are distinct, then duplicator has a winning strategy. Right? If the spoiler can actually force the duplicator to show that they are distinct, then spoiler has a winning strategy. So as an example, let us say that L is equal to the language with the empty vocabulary, and then the structure is of course a set. Suppose you have two sets, let us say A and B with cardinalities at least n. Then duplicator has an n round winning strategy, that is A is n equivalent to B. So how do you show that? Suppose I rounds we have played, right, been played in the game so far, right? Only I rounds. Okay, let us say A1 to AI and B1 to BI. I can be 1, right? And now current position is like A1 to AI and B1 to BI. Then if the spoiler picks some element, right, I want to show that duplicator has a choice to pick an element such that he cannot say that they are not isomorphic, right? So spoiler picks an element, let's say ai plus 1 in A. Now if ai plus 1 is some aj, right, that has been picked before, right, before I, we already came up this element, then replicator returns precisely bj as bi plus 1, because as we noted in the partial isomorphism definition, we want if ai is equal to aj, then bi must be equal to bj. So similarly, if ai plus 1 is equal to aj is chosen, bi plus 1 is equal to bj must be also chosen, right. Now on the other hand, if he picks something which has not been chosen before, then you know that there are, because there is at least n elements, you take the set B and remove the first I element that has been chosen, right, B1 to BA. Out of other than any of this, you pick any other element. That element is an element which is different from something already been chosen, right. So therefore, for his his AI elements, we have BA elements. Now he introduced a new element. I also introduced a new element. If he selected an earlier element, I also select the same element. So that's it, right? And because they are sets, there is nothing else relating them, and therefore that is it, right? So they are basically isomorphic. Two sets of the same cardinality, they are isomorphic. So that is it. So that way we can show that the duplicator has a winning strategy on at most n games, right? Now that is fine. So let us look at another example. Let us say that L is the language with the vocabulary with the linear order, okay, less than simple. Okay, so now let us look at two linear orders L1 and L2, and they have size at least n. Now the question is that is L1 n equivalent to L2? Okay. So one can easily see that that is not the case. Okay, like for example, we give a very small example. Let's say L1 has 3 elements 1, 2, 3, and L2 has 2 elements 1 and 2. Suppose the spoiler want to defeat duplicator. Okay, so what he does is the following. Okay, the spoiler selects the element 2 from the set L1. Okay, so now spoiler has chosen L1, so duplicator has to select some element, right. He has only 2 elements to choose from, right, in B, and he can either choose 1 or he can choose 2. Suppose he chooses 1, right. Now if he chooses 1, what he had said is that 2 is now mapped to 1, right. 2 is equivalent to 1 is what he said. So now therefore the spoiler can now choose an element which is less than the chosen element, which is 2, right, in his structure. So therefore he chooses 1, because 1 is less than 2, the duplicator must be able to present an element which is less than 1, but there is no such element, right, because there are only 1 and 2. He already picked 1, therefore he cannot do that. But on the other hand, if he chose 2, right, then the spoiler can pick 3, because 2 is the maximal element in his set, right, in L in L2, but 2 is not, and therefore in L1, therefore he can pick 3, and there is no answer to that, right. So in the first move, spoiler chooses 2 in L1, duplicator has to respond with either 1 or 2. If he chooses 1, then spoiler will choose 1 in L1, right. Duplicator loses, because if he picks 2, spoiler chooses 3, and therefore again duplicator loses. So in a 2 move game, he will lose, duplicator loses. So therefore this is not true. But on the other hand, right, so we said that if our assumption is that there is at least n elements if they are n equivalent. But on the other hand, if they had too many elements, way too many elements, right, suppose we had let us say L1 and L2, right, had at least 2 raised to n elements. then the claim is that they cannot be shown to be distinct in an n move game by the spoiler duplicator cannot be beaten. Okay, so I want you to think about this. So this is the theorem, right? Let's say that k is let's say greater than 0, L1 and L2 are linear orders of size at least 2 raised to k. Then L1 is k equivalent to L2. Okay, so if you have at least 2 raised to k elements, then they are k equivalent. So as a homework, I want you to think about this and try to see how to prove it. Okay, and if you are not able to, you can also try to read from a book I suggested in the first part of first classes or something, right? Leonard Lipkin, finite model theory. So in this book, page 29 and 30, there is a proof. Okay, so you can also look at that. Okay, it's a very interesting proof. You definitely should look at that. Okay, now another example. Let's say that A and B are graphs. Okay, so A is the graph A1 A2, B is the graph B1 B2 B3, and A1 A2 is an edge, B1 B2 B3 forms a 3 cycle or a complete graph on 3 vertices. Now duplicator can win on a 2-round game is the claim, right? Because spoiler picks any element, duplicator can just pick any other element, that is okay. There is no relation to talk about here. So if he picks A1, he picks B1, or if he picks B3, he will again pick A2 or A1, something like that in the first move. In the second move, spoiler picks a different element, then duplicator can pick any different element from here, and they will still be a partial isomorphism because these two are in the edge relation, any two here and any two distinct there also, right? If he picks the same element, of course he can pick the same element, that's also fine. Therefore in a 2-round game, duplicator can always win. Now what about a 3-round game, right? 3-round game, one can see that the spoiler easily wins because he can just choose the structure B, select these 3 distinct elements. There are no 3 distinct elements here, so therefore he cannot do that, right? The duplicator cannot win. Now what about this one, right? So here are 2 different graphs, like 3 cycle and a 4 cycle. Now what is the minimum number of rounds so that spoiler has a winning strategy? That is the question, right? Like 4 or 3 or 2 or 1 or whatever, right? Whatever number is the rounds, so that spoiler has a winning strategy, and you have to explain why by showing that okay, within less than this there is no winning strategy for spoiler, that duplicator can win. And if there is at least this many rounds, then of course spoiler can always win. Okay. So try to come up with a proof for this. So this is homework, you must submit that. There is another example to look here. Let's say that there are 2 paths, right, path graph on 6 vertices and 7 vertices. Now the claim is that on a 2-move game, duplicator has a winning strategy, and a 3-move game, spoiler has a winning strategy. Okay, I think the first part will be very easy. 2-move duplicator winning strategy, right? You have to basically show that for any selection of 2, right, from the spoiler, right, duplicator has a response, right, 1 by 1 response, right? First choice, there is he has to select something, right, without knowing what is the second move, he has to do it, right? So show that you can draw some tree structure like this to show the choices that the spoiler and duplicator can make, and then form a tree and show that okay, at the end what is the situation about partial isomorphism, right? If there is a partial isomorphism, duplicator wins in that path, and if you can show that you can always force a path to reach here, then that is a winning strategy for duplicator. On the other hand, if there is no partial isomorphism at the end, then spoiler has a winning strategy, and if spoiler can force to basically reach one of these nodes, then he has a winning strategy. So therefore you can draw a tree like this. So the tree here I have given, right, is a winning strategy for the spoiler in a 3-move game. Okay, so the spoiler can start with the central vertex of B, which is B4, and then according to any other choices that duplicator can make, here are the responses in the tree structure. Okay, so you look at that and say that every time it reaches the last choice, right, that basically is a partial isomorphism, right? The chosen elements A1, B3, A2, B5, etc., right? So they form a partial isomorphism. So show this, finally write down this proof, right, formally, right? Basically show first that a duplicator has a winning strategy in a 2-move game by listing out all these possibilities in a tree-like manner, and similarly show that spoiler has a winning strategy by analyzing this tree and show that each of these is basically a partial isomorphism. So you can write down these two and submit that. That is also a homework. Now, to wind up, I want to just mention something which is very much related to these things that we are doing. Okay, so what is called quantifier rank. So quantifier rank of a formula is the depth of the quantification nesting. How many times, like you can always convert all the quantifier to the same type if you want, right? And I mean, it doesn't matter actually, but uh, right, like now, what we can say is that okay, if you know in within the same formula there are like n existential quantifiers nested each other, like one applying on the other, applying on the other, etc., etc., right? I'm not talking about the conjunction or disjunction of two existential formulas, but when you have a nested sequence of things which applies to within the bracket, right? So in that case, if there are k of them in the sequence, then there is a depth k formula, okay, with quantified rank. So, well, you can define it inductively like this: phi is atomic, quantifier rank is 0. If phi 1 and phi 2 are two formulas, quantifier rank is the maximum of the quantifier rank of phi 1 and phi 2. Quantifier rank of negation phi is the same as quantifier rank of phi, and quantifier rank of there exists x phi is quantifier rank of uh, q. I mean, quantifier rank of phi plus 1. I think it should be phi. I wrote it by mistake. I think it's not q. Quantifier rank of phi plus 1. And similarly, it's equal to quantifier rank of roll x5 also, because it doesn't matter. You can just put it in negation, that it will be the same quantifier rank. So here is the quantifier rank. Now the thing is that we can define the first order on of k as the formulas, collection of formulas of quantifier rank at most k. Okay. Now if you talk about f of k, we can see some connection between, we looked at L of 0, L of 1, etc., right, in the earlier thing, right? Some connection is there. So, and that connection is concrete here. So the EF theorem says that, this Ehrenfeucht's game and Fraïssé's theorem can be connected. So you can look at the Fraïssé's theorem that you read before, it, at least I asked you to read, and that is an algebraic characterization. Now there is a game theoretic way of expressing that, and these two are basically connected. Okay, and using this notion we can formalize it. So A and B are two structures on a logic with no function symbols and in the vocabulary. That is, it's a relational vocabulary. Then the following are equivalent, right? If A and B agree on f of k, then that is the same as saying that A and B are k equivalent. Okay? So the k equivalence that we talked about, right, in the duplicator spoiler game, right, in the EF games, there are k round games that are being played which cannot distinguish, right, is the same as saying that, like, formulas agree on I mean the structures agree on formulas on at least k quantifiers, right. This is basically like, one can intuitively see why, right, because the quantification basically is choosing elements, right? And here basically the spoiler and duplicator does are also choosing elements. So basically, if there are k quantifications, then k choices can be correspondingly made, and that basically can be translated to a kind of game, right? That is what we are doing here, right? So the k rank equivalence is precisely the winning strategy for a duplicator on a k move EFK. So I think I am not going into any more details. So as a corollary to this, we can just see that a property, something we already saw, a property P of a finite L structure is not first order definable if for every k in the natural number we have finite structures ak and bk such that ak is k equivalent to bk and ak has property P and bk does not have. Okay. So what we do in using the EF games is precisely to use this property, right? And to show that some property is not definable in first order or can be defined, right? In within FK, something like that. So that is the idea. So with that, I think we will stop, and we really don't need to take any more classes. I think we have covered whatever we wanted to, even though some of them may be not in very detail. But I think you have got a pretty good idea of the kind of things that we look at in the study of logic, and what kind of questions that we ask, right, are interested in. And basically we can stop now, right? You are not going to study logic as a thing, then you don't really need anything more. You just need to understand, how the attempts are being made to make things formal, right? The proof concepts of these things, proving equivalence in structures, all kind of things that we attempt in mathematics are basically formalized by our logical uh, logicians, right? In introducing these kind of concepts, the concepts of proofs and things like that. And with that, we will stop. And any further questions or something, you can always contact me, and you better contact within this week, because next we are going to have our final exam, right? The last of our take home tests will be next week, and with that I think we can conclude. Okay. I think some of you have not really submitted all the assignments, so which means that is going to affect your final score. You cannot do anything about it now, right? As I told you, I cannot really accept things delayed so much, right? And unless you have even informed me what was the issue earlier, that then I don't want to accept any more excuses to not have submitted the answers in time. Okay. So but I think whatever is submitted, people have done reasonably okay. Not everybody has done everything correctly or anything, but that is okay. As we said, we are not going to look at each and every question solved completely. Okay, we will look at some choice of this, and see that, in each assignment, if you have done at least 50% of them very well, then you get a good mark. And otherwise, according to your performance, we will put a weightage to that, and that will be counted and added together in the final marking. Okay. So but I believe that, from looking at the things, like many of you have done reasonably okay. Some of you have done exceptionally well, like at least one or two students reasonably quite well, submitted many of them and correctly. But that is all fine. I mean, this is to be expected. And let us hope that you finish this and finish all the lectures in time, and then next week we are going to have our last of your take-home exam. And with that, I stop. Any questions, please feel free to contact me. And that's it. Okay. See you later.